Hello and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and today we're going to be doing Unit number 11, Lesson number 4.5 on the optimal design of an open box. Just a little comment on the weird lesson number. This was a lesson that I decided to stick in last year, so that was the second year of the course, so I just haven't renumbered the lessons yet. I'm sure we'll be able to roll with it. Today we're going to do something that I think is kind of fun. What we're going to do is we're going to try to figure out the biggest volume of a box that we can make that's open, so it's got no lid. And we're going to make it in a very specific way. So let's talk about that. One way to make an open box is to take a rectangular sheet of paper, something like this, or cardboard, cut squares out of the corners, right, and then fold along creases, something like this, into a box. So for instance, I have a nice tactile one right here. Here's a piece of 8.5 by 11 paper, peekaboo, that I have cut out 2-inch by 2-inch squares. We can then fold up those sides and create a box, all right, something like this. And we can ask, well, what is the biggest volume we can possibly get? Now, before we do this, I'd like you to do a little calculation just to make sure you really understand how this goes. So, let's say that I had a piece of paper that was 8.5 inches by 11 inches, right? So your standard sheet of paper. Okay, and let's say that I cut out squares that were 2 inches by 2 inches, like that, right? So that I got this box. Right. The question is, how many of these cubic inches, if you haven't seen a cubic inch lately, that's inch by inch by inch, how many of these things would fit inside, right? Do that calculation really quickly, and then we'll talk about it, okay? But pause the video now. All right, let's take a look. So hopefully, I'm kind of hoping you all got 63 cubic inches, right? Here's why, of course. When you fold it up, what happens is that the height of the box becomes that 2 inches. Of course, this dimension then is going to be that 8.5 inches minus not 2 inches, but 4 inches, right, from each side. So we're going to get 4.5 inches. Likewise, this dimension now is going to be that 11 inches minus 4 inches. So 7 inches. And then, of course, if we take our volume formula, which is the base times width times height, and we just multiply all these out, we get 63 cubic inches. All right? Now, we could jump right into the calculus and try to figure this out, but I'd like us to play around with this problem a bit. It's one of the last formal optimizing problems we're going to really do together. So let's now start with a piece of cardboard that is 20 inches by 30 inches. So I'm gonna scrub this out. So now we've got a piece of cardboard that is 20 inches by 30 inches. All right. We want to figure out the maximum volume that can be created. What are the dimensions of the box? And we want to round our volume to the nearest cubic inch and our dimensions to the nearest tenth of an inch. Okay. So I'm going to advance the slides a little bit. All right, because what I'd like us to do is start by just looking at the pattern. In other words, what happens if we cut an inch out of each side? Now remember, what we've got going on here is we've got a sheet of paper. Maybe I'll draw it in landscape orientation. Isn't that what it's called? It's drawn like this. Oh, that looks terrible. Anyway, 20 inches by 30 inches, right? And what I'd really like to do is think about, well, all right, before I start setting up any kind of real calculus and equations and things, let's just play around with this. Ultimately speaking, though, you have to nail down one thing right in the beginning, which is what does the volume really depend on? So pause the video now and think about what the only variable in this problem really is. Did you figure out that it was the cut length, right? So if we sort of define that to be, I don't know, let me call it x, right? The amount that we cut out, well, then we can kind of think about what the length is, what the width is, what the volume is. I'm sure for us, we can go right to this volume, right? So let's say that I have a cut length of 1 inch, right? Well, what do I have? I now have a height that's 1 inch, right? I have one of the dimensions, which is 20 minus 2 of those, and then 30 minus 2 of those. So 1 by 18 by 28, what does that give me? It gives me 504, maybe we'll just put it up here, cubic inches. We'll call this inches, right? The 2-inch scenario is kind of what we did last time, except we did it with a different size sheet. So like if I had 2 inches, right, then what would that be? It'd be 20 minus 4, which would be 16. 30 minus 4, which would be 26. And if we multiply all that out, we'd get 832 cubic inches. So a difference. Anyway, do that for, I don't know, a few more. See how many you can do. And then let's revisit it. Take a look at the data. Then we'll go on and do some calculus. All right, let's go through it really quick. So let's see, what do we have? At 3 inches, 3 inches, we'd have a height of 3. Let's see, that 20, we would be subtracting off 6 now to be 14. That 30, we would be subtracting off 6 to be at 24. 3 times 14 times 24 gives me 1,008 cubic inches. If I went with 4 inches, right, then I'd have a height of 4. I'd have 20 minus 8, which would be 12. I'd have 30 minus 8, which would be 22. And that would be 1,056. We keep going up. Notice this. Is it ever going to come back down? 5 inches. Let's see. We'd have a height of 5. Let's see. We'd then have, get rid of 2 of those and 2 of those. Oh, nice. Nice round number. 1,000. Oh, look at that. That one's lower. And let's just do the 6 inches to take care of it. We could keep going, but let's see. Subtract off 2 of that, 18, and 864. And we could just keep doing it, right? Now notice, we don't have something necessarily quadratic going on here. You know, then you'd expect to see some symmetry. I certainly should be very wary of making any kind of real conclusions like this being my maximum. You know, my max has to come in here, or my maximum has to come in here. Right? That's kind of Rolle's theorem if you think about it. You know, at some point in time between the 1,056 and the 1,000, we're going to hit 1,008. So there's got to be a maximum somewhere in there, you know, somewhere between 3 inches and 5 inches. It's not going to be 4 inches. It's not going to be that nice, right? But what doing a table like this really gives us a sense for is how the calculus is going to play out. So let's do that. I'm going to clear out this table, and then we're going to go on and do some calculus. Do you have it? Okay, here we go. All right, now for the calculus. Okay, so this one's a little bit weird in a certain sense because, hey, red. I'm always surprised after I've changed it to red that it's still red. I don't know why. You know, here comes the calculus, right? Here we've got this box, and we're cutting out side lengths of x. And we know that originally this was 20. So, going back to blue for a second, this dimension would then be 20 minus 2x. The original dimension here was 30. So this, well, maybe I'll put it here, will be 30 minus 2x, right? And in fact, what we have, right, when we draw this box out, could have been worse. So we have a box that has a height of x, a base of 20 minus 2x, and maybe a width or a length, however you want to call it, of 30 minus 2x. So what's cool about it is that the volume is right now only a function of x. It's x times 20 minus 2x times 30 minus 2x. Pretty nice, huh? Now, we could start to take derivatives, set them equal to 0 right now. It's probably a good idea to use some algebra. So let's make algebra magic happen. We really are going to make algebra magic happen because we're not going to multiply it all out, although it wouldn't be that hard, right? You'd probably FOIL this out, then distribute an x. One way or another, though, the volume function, when all is said and done, looks something like this. 4x cubed minus 100x squared plus 600x. And the beautiful thing is now we are ready to go. We are totally ready to go. So let's take the derivative. It's very easy, right? V prime of x will be 12x squared minus 200x plus 600. Ooh. We want to figure out where our horizontal tangent lines are. Now, I know that we've all been biased towards factoring, and if not factoring, the quadratic formula. This is a quadratic equation that can only be solved by either the quadratic formula or by a graphical solution. Because of that, I would suggest doing it using a graphical solution. So what I want you to do is take a minute and solve this graphically. Okay, and there's going to be two solutions, two viable solutions. So solve this graphically, or at least two solutions that appear viable. Okay, get me 3 decimal place accuracy. All right, well, it shouldn't have been too hard. We solve it and we get x equals 3.924, and that's in inches. And the second root, no great surprise, right? 12.743 inches. No great surprise in terms of there being 2. I mean, it is quadratic. Now, what's a little bit weird is that with most of the optimizing problems that we've had so far, there tends to have been only one critical value, or one viable critical value. So we've had all sorts of tools like first derivative number lines and second derivative concavity to justify which is which. But the problem now is that we have 2. All right, so the question is, well, what do we use? What's our analysis? What should we go with? In this case, actually, an endpoint analysis works quite well. So let's take a look at an endpoint analysis. Now, remember, to do an endpoint analysis, what you really need is you need some endpoints. So what number is here and what number is there? I'd like you to think about that for a minute, all right, because it's kind of cool. You might have to think about it in terms of just real world. Just think about this. If you were making this box, what is the smallest cut you could make? And what is the largest cut you could make? Take a moment. All right, let's go through it. I'm going to erase my lovely question marks here. Okay, go back to my pen mode. Well, the smallest cut I could make is 0. Now, it's a very uninteresting cut. It's a very uninteresting box. In fact, if you think about it, it's simply a box that is a flat sheet of paper, right? If I don't make any cut at all, I can't fold up the sides. Now, what's kind of cool is you might say, well, then the biggest cut is 30. Well, it certainly isn't 30. In fact, the biggest cut is 10, right? Think about it for a minute. That is the absolute biggest square you could cut out because of that side of 20. Now, what's awesome about the endpoint analysis, especially this guy, is that it immediately tells you that this is not a viable solution. All right? And we're basically there at this point, because we can figure out the volume at 0, right, by just substituting this in here, into here. No great surprise, that's 0. We can also find the volume at 10. That's also going to be 0. And the volume at 3.924 must be my maximums because those are my minimums. And that ends up being 1056.306, or rounded to the nearest cubic inch, 1056 cubic inches. I'd also like the dimensions of the box. That would be 3.9 inches by, and now I can figure out the other two. The other two aren't that hard, right? All I would have to do is go up to here and take 20 and subtract twice x, and 30 and subtract twice x. And they're not the prettiest numbers on earth, but they'll be 12.2 inches and 22.2 inches. So we've got, and I decided to switch my convention midway through. Maybe I'll just make that a big dot. So we've got our box, we've got it, made it as big as possible, and we found the largest volume, which is awfully cool. All right, I am going to clear all this out. Got it? Okay, here it goes. All right, I think I might have an extra page in case that spilled over. Yeah, just like a blank sheet. Hi, I feel like I can do a song, a dance on this sheet, do some freeform scribbling, you know, make my favorite guy who clearly needs a little bit more artwork on it. Okay, I've wasted all of your time here. Let's make him a little bit, we'll make him cool and hip. Clear him out. I had to use that page, otherwise why did I put it there? Okay, let's finish up. It's a single problem. That's all we're doing. In fact, the next lesson is going to be a single problem, and then we are done with optimizing. My students are going to have a giant optimization packet, but there's really nothing new to learn. So that's it. We designed an open box, and there's no homework on this one for at least my students. We'll come back to that in the next lesson. Anyway, for now, let me just remind you, this has been an Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and until next time, keep thinking,